In this mini-sketch, we'll talk about the regulation of PFK1 and FBPase1 in more detail. This scene takes place in the exclusive security control room at Sketchyland. The security team monitors any illegal and suspicious activity happening in the park. In the last few weeks, there hasn't been much going on, except for some kids vandalizing the animatronic pirates from Davy Jones's candy locker. They apparently just love pulling out pee batteries and posting videos on social media. Like, the internet just keeps getting weirder. Today, we'll be monitoring any suspicious activity going on inside Pirates of the Caribbean and Davy Jones's candy locker. The bottom of the split screen from Pirates of the Caribbean shows our PFK1 cast member transferring a P battery to the F6P Pirate's 1 peg leg, producing F16BP. The top of the split screen from Davy Jones's candy locker shows our FBPase1 kid using a water gun to shoot the P battery out of the 1 peg leg of our F16BP pirate, producing F6P. Recall that PFK1 converts F6P to F16BP during glycolysis, and FBPase1 catalyzes the opposite reaction, converting F16BP to F6P during gluconeogenesis. These enzymes are directly regulated by fructose 2,6-bisphosphate, or F26BP. You'll see a security laptop that's connected to the monitor on the wall. Right next to the laptop is some 2,6-fruit, representing F26BP. The bottom of the screen now says play and the top says stop. That's because F26BP activates PFK1 while it inhibits FBPase1. So how do we make F26BP? Phosphofructokinase 2, or PFK2, transfers a phosphate group from ATP to F6P, producing F26BP. This is represented by the IT guy with a kind button and a number 2 pattern on his shirt inserting a P battery into a laptop. When PFK2 is active, we produce more F26BP, which stimulates glycolysis by activating PFK1. PFK2 can't be active all the time because if that were the case, then glycolysis would continue on until all the glucose is used up. And we wouldn't want that to happen if blood glucose levels are already low. That's where FBPase2 comes into play. FBPase2 keeps PFK2 in check by catalyzing the opposite reaction, converting F26BP to F6P. FBPase2 is represented by the same guy pulling a P battery out of another laptop. You're probably thinking, Ricky, what are you talking about? I thought he was PFK2. Actually, PFK2 and FBPase2 are part of the same bifunctional enzyme. That's why we use the same IT guy. Both FBPase2 and PFK2 can't be active at the same time. When one is active, the other shuts down. Protein kinase A acts like a switch to turn on FBPase2 and turn off PFK2. When protein kinase A is inactive, PFK2 is on while FBPase2 is off by default. Let's talk about what happens in the fed state, as represented by this partially eaten sandwich. After eating a meal containing carbohydrates, blood glucose levels increase, which results in release of insulin from the pancreatic beta cells. Insulin increases intracellular glucose uptake, which inhibits adenylate cyclase, so we produce less cyclic AMP from ATP. Low cyclic AMP inhibits protein kinase A, so PFK2 will be active. Therefore, we produce more F26BP, which activates PFK1 and glycolysis. The word inside is written on the battery slot where the IT guy is inserting the P battery to help you remember that insulin activates PFK2. We drew some glucose candy next to the word inside to help you remember that insulin drives glucose into cells. You'll also see an ad for Camp Sketchyland, painting, kites, activities on the floor because cyclic AMP and protein kinase A levels go down after eating. In case you didn't know, the first 3 letters of painting, kites, activities is PKA, short for protein kinase A. On the flip side, let's talk about what happens during a fast, as represented by the no food allowed sign. Low intracellular glucose levels stimulate adenylate cyclase to make cyclic AMP from ATP. High cyclic AMP levels activate protein kinase A, and FBPase2 will be active, producing less F26BP. Therefore, FBPase1 and gluconeogenesis will be active. We used an empty candy jar to help you remember that glucose levels decrease during the fasting state. Note the Camp Sketchy Paintings, Kites, Activities poster on the wall because cyclic AMP and protein kinase A levels go up. Prolonged fasts stimulate the release of glucagon from the pancreatic alpha cells. This is represented by the glucagon sweetener next to the no food allowed sign. Notice that the sweetener is sitting on the same laptop that the IT guy is pulling a P battery out of. This will help you remember that glucagon activates FBPase too. Okay, let's wrap up this sketch. PFK1 converts F6P to F16BP during glycolysis. FBPase1 catalyzes the opposite reaction, converting F16BP to F6P during gluconeogenesis. F26BP activates PFK1 and inhibits FBPase1. PFK2 converts F6P to F26BP. FBPase2 converts F26BP back into F6P. PFK2 and FBPase2 are part of the same bifunctional enzyme and can't be active at the same time. After eating, blood glucose levels rise and stimulate the release of insulin, which drives glucose into cells. High intracellular glucose levels inhibit adenylate cyclase, so less cyclic AMP is made. Low cyclic AMP inhibits protein kinase A, which then activates PFK2. Therefore, more F26BP is made, which activates PFK1 and glycolysis. In contrast, during a fast, glucagon is the predominant hormone. Low intracellular glucose levels activate adenylate cyclase to produce more cyclic AMP, which activates protein kinase A and FBPase2. As a result, we make less F26BP, so FBPase1 and gluconeogenesis will be active.